computer. Okay. Okay, so we're recording, which probably has no real bearing. Okay, yeah, so part 2 is going to be a recitation. So this is just going to take place in Gather. So in the auditorium where you are right now, I guess, in Gather, there's these little tables. And what we recommend is that you like sit down at a table, find some friends, or meet some new people and work on this problem set that we've prepared. The problem set is about breaking down the steps to analyze 2 algorithms that one is going to present to you in the first part. And obviously this is ungraded. We can't, it has no bearing on anything. It's just for you to learn. And we also have solutions, so feel free to look at the solutions when you want. There are going to be 6 TAs. It's me, Wen, Chris Dan, Fei Fang, Christina Lee Yu, and Andrea Zanet. These are all like experts in this area. And they'll be around, they'll walk around from table to table. They'll be around to ask questions, to talk about other stuff that you want to talk about. So that should be quite fun, and we hope it's interactive and you enjoy it. And then part 3 will be back here in Zoom, and I guess we'll announce in Gather when we're going to start that. So with that, I'm going to hand it over to Wen, who's going to start off with the part 1 of the tutorial. Wen, take it away.
Okay, great. Thanks, Akshay. Hello, everyone. So I'm going to cover the first part of this tutorial, which basically covers the fundamentals of Markov decision process and 2 simple algorithms that we're going to analyze in the recitation. Okay, so I want to start from the practical motivation, right? So reinforcement learning actually has a long history. So about 30 years ago, researchers have been using reinforcement learning techniques to solve those board games. The TD Gamma is one great example. And recently, people have been using techniques from deep learning and reinforcement learning together to solve this extremely complicated video game, StarCraft. And more impressively, we have been using reinforcement learning techniques to solve real-world problems, such as the bottom 2 listed in this slide. The first one is the balloon navigation, and the second one is robotics dextro manipulation. Right? So there's a good application. There are good applications for reinforcement learning, and I think this is a good motivation, for us to spend time and effort to study reinforcement learning. So what is reinforcement learning? Right, so we can abstract reinforcement learning into this 2-agent, 2-player environment. So we will have this learning agent, and we will have this environment. And the learning agent basically going to look at the environment, and based on the status of the environment, determine an action and recommend the action to the environment. And once the environment receives the action, it will send a 1-step immediate reward, maybe a reward signal describing how good this action is, conditioning on the current state of the environment, right? And then it will also evolve to the next state, right? So conditioning on where it was and conditioning on the action that it received, it will evolve to the next state. And it will also send the next state to the learning agent. And then this loop goes on for many, many time steps. Right, so now you can imagine the goal of the learning agent is actually to find a good mapping that maps from state to action, right? That maximize the expected total reward of this, whole process. And in this framework, the environment could be something very complicated. For instance, a self-autonomous driving car system, right? So here, your learning agent will be, the self-driving system. And it could also be a human, right? Here, the learning agent might be, some personalized education system that is trying to optimize some utility functions. Okay, so great. So why reinforcement learning is hard, right? So we're gonna look into the 3 components: credit assignment, generalization, and exploration. So the claim is that if you want to solve these 3 components in one shot, this is actually a pretty hard problem. And in the third part of this tutorial, I'm actually going to talk about some preliminary results on, at least trying to solve these 3 components in one shot. Right. So, but if you just look at 2 out of these 3, we kind of understand them reasonably well. So an example is that if you look at credit assignment and generalization, there are approaches that can do these 2 at the same time. For instance, the policy gradient approach that we're going to talk about today, And there are also structural prediction and imitation learning problems fall into this category as well. And if you look at exploration and generalization, we have contextual bandit, right? So here you only make one-step prediction. So you don't need to worry about credit assignment because the outcome is just associated with the one action that you just made. And if you look at the credit assignment and exploration, this is mainly about how to learn in discrete Markov decision process where the number of states and number of actions are small, right? So you afford to actually try all the actions and all the states, right? There's no need to do exploration because the number of states, number of actions are small. Right, so in the first part of the tutorial, we're going to focus on how to learn in tabular area, how to learn in small size Markov decision process, and how to do policy search. Okay, so the plan for the tutorial, first part, as I said, we're going to focus on tabular setting, basic concepts of Markov decision process, then the policy optimization approach, and then an exploration algorithm. And then we're going to move to recitation, and we're going to talk about the proofs for the policy gradient approach and the UCBVI algorithm, the exploration algorithm. And then finally, actually, we'll talk about recent advancements in terms of trying to solve the 3 points in the previous slides in one shot. Okay, so let's move into the first part, the basics of Markov decision process. Okay, so let's define Markov decision process. So this is the framework that we're going to stick to throughout this whole tutorial. We're gonna define a policy pi. So this is a mapping that maps from state of the environment to an action. So let's think about this as a stochastic policy in the sense that you map from a state to a distribution over action space, right? So think about this as a classifier. You look at the state and treat each action as a class, right? So this is a multi-class classifier. And the setting that we're going to look at right now is actually the infinite horizon discounted setting, which means that you're going to interact with this environment for infinite many steps. Right, so we're going to use this function to denote the reward. So given a state action pair, what's the reward that you get? What's the one-step immediate reward that you get? Right, so this is a Markov in transition. As you can see, the next state S prime is only depend on the current state and the action that you get. Okay, so we will denote this as the initial state distribution, meaning that at the very first step of this infinite process, you sample the first state from this fixed distribution. Right? And importantly, for this setting, we have a discount factor, which basically says that I'm going to discount the future reward. Right? I'm only going to pay more attention on the current, more recent reward. So in other words, this is the objective function that we care about. Right? So the objective function is the expected total discounted reward. So here we discount the reward at time step h by this discount factor gamma to the power of h. Right? So this is our objective function. This objective function has an expectation. So this is an expectation with respect to all the randomness from the initial state, the randomness from the policy, the randomness from the Markov in transition. Right? And our goal is to find a policy that maximizes this objective function. Okay, so this is the infinite horizon discounted setting. Now let's talk about some definitions, some notations. So the first notation is the state action distribution. So let's define this quantity as the probability of this policy visiting a particular state action pair at time step h. So imagine that you have a policy pi, right? And you executed this policy pi in the environment, and you ask that, at time step H, what is the probability of, this policy hitting a particular state action pair? Right? And now we have infinite many steps, right? So we have infinite many such distributions. So let's define a mixture distribution, which is the average state action distribution. That is the average of all these distributions over different time steps. And we discounted it properly. In other words, for time step H distribution, we discounted it by the power, gamma to the power of H. Right? And you can show this is still a valid distribution, and this is for normalization purpose. Normalization purpose. And because of this normalization factor, now this distribution is a valid distribution. Right? In other words, if you sum over OSA, this is equal to 1. Okay, and we're also going to abuse the notation a little bit and sometimes write this just over S. Right, so this is a distribution over state only, and by just marginalize over the action. Okay, so 2 more definitions, then we will be done with notations and definitions. Okay, so the value function. So let me first describe, what it means in words. I saw a question. So good. Mu is the initial state distribution. So in other words, d pi mu 0 SA will just be mu S, right? Because this is at the first time step times your policy pi AS. Right. Definition. Okay, so back to value function. So we're going to use this notation v pi s as the value function. So in words, this says that what's the total expected reward when starting in state S and following policy pi all the way to the end, right? Imagine, you put the agent in state S and then you ask it to follow policy pi all the way to the end. You ask what's the expected total reward that you would have got. So this is represented by this function. And now, in terms of mathematical equation, this is pretty much just describing what I just said, right? So imagine that you start from the state S, all right? And then you follow policy pi all the way to the end. What's the expected total discounted value, right? What's the reward to go? What's the expected reward to go? And if you don't want to write this as a sum of infinite many terms, you can actually use the Markovian structure and write this as a sum of 2 terms, right? So the first term is essentially saying that what's the reward that you would get if you follow this policy pi for 1 step, right? And then you're just going to say basically the rest of the total reward is the expected total reward to go starting from the next time step, right? You're just splitting this whole process into 2 stages. The immediate 1 step and the whole process starting from the next time step. And then you sum the reward from these 2 components together, and now you get this value function. Right? Similarly, we can define this Q function. The difference is that now we have an action here, right? So think about this process as, I'm starting at state S and I'm going to do action A. All right, once I do action A, I'm going to follow policy pi all the way to the end. And what's the expected total reward of this whole process, right? So in equation, this is essentially saying that I'm going to start at state S and I'm going to do this action. I'm going to execute this action, right? So instead of following pi, I'm just going to execute this action. And once I'm done with this action, I'm going to follow my policy pi all the way to the end. What's the total expected discounted reward? Okay, so again, you can write this equation as, you can write this value as a sum of 2 terms. Again, this is the 1 step immediate reward, right? Like how much reward I get if I just take action A at this state, right? And then the second term is essentially saying that what's the expected reward to go that you would get starting from the next time step.
Hey, when there's one question.
Yes.
So Debamita asks, what's the significance of gamma?
Yeah, so gamma is the discount factor. And if you look at this infinite horizon setting, right, if you don't discount it, then your total reward might be infinite. And so if you discount it, we sort of normalize the total reward from 0 to 1 over 1 minus gamma.
Yeah, so this is somehow like capturing how much you care about things happening right now versus things happening in the future. So, if I gave you like $1 today versus $100 in 10 years, which one would you prefer? Right. And that's sort of the discount factor is navigating this trade-off.
Okay, great. So now we can talk about some properties of Markov decision process. Okay, so the first property is the optimality policy, the optimal policy. So given the Markov decision process, you can always show that there exists a deterministic stationary policy pi star that maps from state to action. It's a deterministic mapping, right? It's not a stochastic policy, such that the value function of this optimal policy dominates any other policy's value function, right? So this is for all s and all pi. Great, and we're going to denote V star as V pi star and Q star as Q pi star. Okay, so this is just one notation simplicity. And we're not going to prove this theorem. And if you're interested in how to prove in the existence of such deterministic stationary policy, you can look into the RL monograph, whose link is on the tutorial website. Okay, so one important property is this Bellman optimality, right? Which is essentially quantifying the relationship between Q star and V star, right? So on the right-hand side, on the left-hand side, we have Q star, and the right-hand side is essentially trying to rewrite this Q star as a sum of the two terms, right? The first term, again, is the one-step immediate reward. Like how much reward you got if you take action A at state S for this particular step, right? And the next component is essentially saying that what's the maximum total reward that you would have got starting from the next time step, right? Assuming that you act optimally afterwards. And more importantly, if you plug in any function Q that maps from state action to a real number, right? And if you find that this Q function actually satisfies this Bellman optimality equation, in the sense that you have a function Q here and you have Q here. If you find a function that satisfies this, then you're guaranteed that this Q is actually equal to Q star. Yeah, so I saw a question saying that, is this stationary deterministic policies V star dominates all non-deterministic policies? Yes, and it also dominates some non-stationary policy in the sense that policy depends on the history as well. Right, so in other words, like if you're working on Markov decision process, there's no need to look at a history-dependent policy because your optimal policy is only going to look at the current state and make a decision. Okay. Okay, so now we're going to move on to two planning algorithms. By planning, I mean, if we know the transition P, right? If we know the reward function R, how can we search for the optimal policy pi star, right? We know that there exists one. How can we find it? There's no learning involved at this moment. Okay, so everything is no. It's just a planning and a computation problem. All right, so the first algorithm we're going to talk about is value iteration. So this is going to be a fixed point iteration approach. Right, so let's just first define this Bellman operator. And the Bellman operator is a mapping that maps from a function to a function. Okay, so this is a definition of Bellman operator. It takes this function as input, right? And after you apply Bellman operator, you get back another function that maps from state action to a real. And the new mapping is defined such that if you take a state action pair as input, and this is the scalar that you're going to output. Right, so I'm just defining a mapping that maps from a function f to another function. Okay, so if you remember the Bellman optimality, it says that the Q star is actually a fixed point solution of this Bellman operator, right? T times Q star is actually equals to Q star. So that's the Bellman optimality that we just saw from the previous slides. Okay, so that basically suggests an algorithm, right? So we define a mapping Bellman operator, and we know that the thing that we're trying to search for, the optimal policy's Q function, is a fixed point solution of this Bellman operator. So why don't we just keep iterating, right? And hope for a convergence for this fixed point iteration procedure. That's exactly what this value iteration algorithm does, right? So you initialize some mapping Q0 that maps from state action to a real from inside this range. Right? So the reason that we do 1 over 1 minus gamma is that a reward signal is from 0 and 1. And because we're just doing discounting, so the maximum reward that you're going to get in this infinite many steps is 1 over 1 minus gamma. Right? And then we just iterate. We just do this fixed point iteration. All right, so that's the algorithm. And in terms of theorem, you can show that after t iterations, you will find a policy pi t whose value is very close to pi star up to gamma to the power of t. Right, so you find a pretty good policy. The optimality gap is roughly gamma to the power of t. And the way we prove this is basically trying to show this fixed point iteration is a contraction map. Right, so for any q and q prime, if you apply this Bellman operator in front of them, and then computing the difference between these two new outputs, the distance is less than the distance of the previous two and q prime. Right, so this is a contraction map, and if you use the contraction map, and if you use this fixed point iteration procedure, right, together with this contraction map, you can basically show that this will converge at the rate of gamma to the power of t. Right, so that's basically the value iteration algorithm. It uses the fact that Q star is a fixed point solution of this process, and it also leveraged the fact that this is a contraction map, right? And then the algorithm is essentially just doing iteration, and you will get gamma to the power of t convergence rate. So the second algorithm that I want to talk about is a more direct approach, in the sense that this algorithm policy iteration going to directly search for the optimal policy. Right, so the way it works is that initialize a policy. Right, I'm just going to work on the policy space. So initialize a policy pi that maps from state to action. And the first step is policy evaluation. In other words, I'm going to compute these Q functions, these Q values for my policy. Right, so remember we defined this Q function for each policy pi, right? And we're not going to go into the details of how to do policy evaluation, but trust me here, we can just solve a linear system and get this Q pi exactly. All right, so for now, just assume that we can do policy evaluation. Given the policy pi t, we can get its Q value for every state action pair. Right, and then we can do policy update. So here, the update is very simple. So basically it says that we're going to reset the new policy to be this greedy action selection operator, right? This is argmax over A. So you look at the current policy's Q value, and you're just going to pick an action that maximizes its Q value. Right? And our hope is that the new policy improves the older policy. So intuitively, this actually makes a lot of sense, right? So basically this says that if at state S, you find an action A such that if you deviate to action A first and then follow the older policy, you realize that this is a better procedure than directly following policy, the older policy pi t, right? Then next time you see this state, you should actually pick this action, this new action, right? Because you find a better, local improvement, right? By deviating to A first and then follow the older policy instead of just following the older policy all the way to the end, right? So if you see this is such kind of state, why not just, choose this better route, right? Just deviate to action A. So that's the intuition behind this procedure. And indeed, you can show that pi t plus 1 is never going to be worse than pi t. And indeed, pi t plus 1 will be better than pi t all the way until you reach to the optimal policy. So in other words, you can show that once pi t plus 1 is not improving on pi t, you're guaranteed to find the optimal policy. And you can also show a convergence rate. Basically, you can show that the difference between the value of pi t plus 1 and the optimal policy, right, will be smaller than the difference between the previous policy and the difference between the previous policy's value and the optimal policy's value, right? And the discount factor and the convergence rate is again related to this discount factor gamma, right? In other words, you're going to converge the rate of gamma to the power of t. Yeah. Okay, so these are the two planning algorithms. So basically, this says that if I give you a Markov decision process with, I review every information, all the information about this Markov decision process to you. I tell you the transition, I tell you the reward, right? So these two algorithms, value iteration and a policy iteration, are basically telling us how to search for the optimal policy. Right? Again, there's no learning involved. Everything is just computation and plan.
When do you see this question? So there's a question about which one of these two algorithms has a better suboptimality gap.
Better suboptimality gap. Okay, so yeah, so one thing that I want to mention here is actually for if you run policy iteration algorithm, okay, so you will guarantee to hit the optimal policy in the number of iterations a to the power of s. All right, so why this is true? This is actually not that hard to say. How many policies you have, right? We have in total a to the power of s many deterministic policies, right? So this algorithm, every round is guaranteed that the new policy will be better than the previous one. Okay, and another guarantee you can prove is that once your new policy is the same as the older one, you're guaranteed to find the optimal policy. Right, so in other words, you keep doing hill climbing, you keep searching over these policies, and the new ones is guaranteed to be better than the previous one. So you only have finite many policies, right? A to the power of s. So you are guaranteed to find the optimal policy after at most a to the power of s iterations, right? So this is the upper bound of the number of iterations. But if you look at the value iteration approach, so this is actually an indirect approach. In other words, the convergence rate, you might not be able to actually hit the optimal policy. Imagine the worst case where the optimal policy's value function values are very close to the second optimal policy's value. Right, so now you need to run this iteration approach. You need to run this iteration approach many, many times until the optimality gap, which is captured by the gamma to the power of t. T is the number of iterations, right? So you wanted this number, the gap, the estimation error, to be smaller than the gap between the first optimal policy and the second, best policy's value. right? So if these two are very close, then you're going to run this value iteration for many, many, many iterations. But the policy iteration algorithm is, regardless of what, you're going to hit the optimal policy at the most a to the power of s iterations. Okay, so there's a question about how to decide when to do value iteration and when to do policy iteration. Okay, so good question. So I think in value, okay, so let's go to value iteration. So I think one issue that I just mentioned about value iteration is essentially, you have to actually, in the worst case, you actually have to run this many, many iterations, right, in order to hit the global optimal policy. But if your goal is to just find, a near optimal policy, right? So this is great. You actually just, because every iteration, the computation is actually not that expensive compared to the policy iteration. So you just run this for gamma to the power of t many iterations, your estimation error is gamma to the power of t. Right? And for the policy iteration approach, so we skipped this policy evaluation step. But if you naively do this by solving this linear system, you're going to pay the power of the computation is s cubic, right? So which is a little bit expensive if you want to do the exact policy evaluation, right? But the good thing about this policy iteration is that you guarantee to hit the optimal policy in finite number of iterations. Okay, so so we have been talking about infinite horizon setting, right? So now let's just talk about another setting, which is the finite horizon setting. So basically they're the same. The only difference is that instead of doing infinite many iterations, we're doing finite number of iterations, right? So the number of interaction that we're going to make with the environment is capital H. All right, so the setting basically works as this. We always sample the initial state from this initial state distribution. Every time step, take action A and observe new reward and transit to the next. And we repeat for capital H many steps. And then the objective function is basically the same, except now we're just going to look at the expected total reward over capital H many steps. Right? No discount factor anymore. Right? So this is a finite horizon. And one caveat is that now the optimal policy and the optimal VQ functions will be time dependent. Right? So if you see the same state at the first time step and the same state at the last time step, of course, the optimal action will depend on your time, right? If you're at the last time step, there's no need for you, to be strategic or whatever. Just because you're at the last time step, just pick the action that achieves the highest reward, right? But if you were at the beginning, you may have more freedom to sort of do some strategic stuff, right? Okay, so summary so far, we talked about the MDP definitions, right? State action distributions, value and Q functions, and tree planning algorithms. Okay, so I just want to quickly go through part 1B, which is policy gradient approach and a natural policy gradient. And particularly, we're going to analyze natural policy gradient in the recitation. Okay, so the motivation policy gradient is that this has been widely used in practice, right? So pretty much in all these applications, we use some sort of policy optimization, policy gradient approach to optimize for the policy. And another motivation is actually it's simple, right? So think about this as a differentiable classifier, right? Again, actions are classes and states are input, right? So think about design a neural network with softmax layer, right? So here the parameter theta represents the weights of the neural network. So now you can actually just express this total expected reward, right, as a function whose parameter is theta, right? And we are trying to optimize theta. We're trying to find, the best classifier that achieves this choose the highest total expected reward, right? And now if you were able to compute the gradient of this objective function with respect to the parameterization theta, then just do gradient ascent, right? And the hope is that gradient ascent can just find a very good policy. So algorithm-wise, this is just the algorithm, right? Gradient ascent, that's it. And there's a nice theorem telling us that we actually have a pretty simple closed form expression for the policy gradient, right? So one more last notation, and I promise this is the last notation. So let's define this advantage function, which is the difference between Q and V, right? So the reason that in literature we call it advantage is it's essentially sort of quantifying, what's the advantage of deviating to action A at state S, right? Comparing to, directly following policy pi, right? So we are computing the difference between two procedures, right? So the first procedure is taking action A first and then following policy pi. The second procedure is essentially just following policy pi all the way to the end. So we are sort of, this advantage function is quantifying, what's the benefit of deviating to action A at this step, right? So the policy gradient theorem is essentially saying that we should actually adjust the parameters of the policy such that the next round, our policy is going to put a little bit more probability mass on those actions that have high or positive advantage. Right, so this kind of makes sense because this is doing sort of local search, right? If I realize that at this particular state S, I have an action A that gives me positive advantage, why not just, adjust the policy so that next round your policy put a little bit more probability mass on those good actions. And so this is essentially what policy gradient is trying to do. Okay, so now I want to talk about the global convergence of policy gradient approach. All right, so let's just go back to the discrete Markov decision process, and let's use this softmax parameterization to represent the policy. So basically for every state SA, I'm going to design a parameter, right? This is a parameter that I'm going to optimize, and I'm just going to add softmax on that, right? So this is a valid distribution. So pi theta is a distribution over action space, okay? And I'm not going to go into the details of this derivation, but you can actually show by using this softmax parameterization, you can show that the derivative of the value function, right, with respect to a particular parameter, theta SA, can be written in this very simple fashion. Right? And then you can just do gradient ascent to maximize the objective function. And the nice thing is that despite being non-concave, the objective function is non-concave in general, we actually have global convergence. Right? So the theorem here essentially is saying that under the condition that your initial state distribution has good support everywhere. Right? So this is a strong assumption, but you can also show that this assumption is not avoidable for proving global convergence of this approach. So if my initial state distribution has support everywhere, then this algorithm policy gradient ascent with exact gradient actually going to converge to a global optimal solution, right? Despite that the objective function is actually non-concave. Right, so this is a nice property. But the convergence rate of this policy gradient approach is actually pretty slow. Particularly, it will at least depend on polynomially with respect to the size of the MDPs. Right, so the rate is probably poly S, 1 over 1 gamma, poly A, poly mean over S, 1 over mu S times 1 over T. Right, so which could be very bad if your MDP is very big, and it could be very bad if your initial state happen to have some small support in some states, right? Because this depends on mean over 1 over mu S, the minimum over S, and then 1 over mu S, right? Okay, so the next algorithm that I'm going to show you is actually will have much better convergence, right? So this is natural policy gradient approach. So the idea here is that let's compute a natural gradient rather than gradient. Okay, so let's define Fisher information matrix. And then let's just precondition the policy gradient, right? Using this Fisher information matrix. And this is the natural gradient. And then let's just follow the natural gradient. Let's do natural gradient descent. Okay, so that's the algorithm. And for simplicity, let's assume Fisher information matrix is a full rank, so we can do inverse. Otherwise, we're just going to do pseudo inverse. Okay, so I want to quickly mention the intuition behind this approach. So you can sort of trying to understand this MPG as a trust region methods, right? So the objective function is we're trying to optimize a linearized version of the original objective function, right? So we take the gradient of the original objective function and write this as a linear function, right? This is first order Taylor expansion of the objective function. And then we have a trust region, which is essentially saying that the new policy's trajectory distribution should stay close to the older policy's one in terms of KO divergence. So here, this is the trajectory distribution. Right, so essentially we are saying that the older policy should not be, the new policy should not be too far away from the older policy, measured by this weird KO divergence between two trajectory distributions. Right, and because this KO might be very hard to deal with, right? This could be nonlinear, non-convex. So what we do is just do second order Taylor expansion on the KL, right? And if you do second order Taylor expansion on KL, you will see actually the second order Taylor expansion of KL is exactly equal to this guy, this new metric, right? So this is a PSD matrix. So now you get a new metric. This is a local metric in the sense that your Fisher information matrix is changing based on where you are, right? But this is a valid metric. This is a symmetric. This matrix, Fisher information matrix, is positive semi-definite at least. Okay, so now just replace your KO constraint by this symmetric new distance, right? And trying to solve this, new programming, this program that has linear objective function and convex quadratic constraint. And if you do that, you will actually reveal the MPG update procedure, right? So MPG is essentially saying that you should do incremental update, right? Make sure, the new policy is not too far away from the previous one in terms of, the KO divergence between two policies trajectory distribution. Okay, so I want to quickly mention the global optimality of this algorithm as well. Again, to do that, we're going to go back to the discrete Markov decision process and look at this tabular softmax parameterization again. Okay, so every state action pair has a parameter. And we can show that this MPG update actually can be written equivalently as this soft policy iteration approach. Right, so we're not going to spend too much time here because in the recitation, we're going to derive this expression. So I'm going to skip this proof sketch. And so the interpretation is that actually MPG, what MPG does is actually it runs this online mirror ascent algorithm per state wise. Right, it initializes an online mirror ascent algorithm at every state and then use the current policy's advantage function as a reward vector for iteration T. Right, so every state you just run a mirror ascent algorithm and use the reward advantage A to the power A, using this advantage as the reward vector at time step T. And your hope is that you can convert the regret of online mirror ascent to the regret of this natural policy gradient algorithm, right? Okay, so in terms of global convergence, we can actually show that if you do this capital T many iterations, you will find a policy pi whose gap with respect to the optimal policy is shrinking the rate of 1 over capital T. Right, so this is pretty nice. And some remarks. This is, as we said, this is a non-convex, non-concave objective function, right? But again, we find the optimal solution here. And different from the vanilla policy gradient convergence, there's no S dependence at all in this gap. Right? And we only have a mild gap logarithmic dependence on the number of actions. And as you see here, there's no assumption on the initial state, right? Different from the PG approach, there's no assumption on the initial state. it applies to any initial state distribution. So this is pretty nice. And this is actually the benefit that you get by doing natural policy gradient versus the vanilla policy gradient. Okay, so I'm going to skip this proof sketch because we're going to dive into this in great detail in the recitation. Okay, so summary so far, we have global convergence for PG and MPG, despite the objective function being non-concave, right? And we're going to talk about MPG convergence with learning and approximation in the recitation. Okay, so the last part, which is about exploration. Again, I'm going to quickly go through the algorithm and the intuition, and we're going to leave the details of the proof in the recitation. Okay, so the motivation is that, if you don't know anything about the Markov decision process, right? How can we actually learn to find the optimal policy? We talked about planning approach, but now we really get into the region where we needed to do learning, right? Because we don't know anything about this Markov decision process. So in order to do that, in the worst case, we really needed to do efficient exploration. So here we have this combination log problem. So often in literature, we use this problem to quantify, the need for exploration. So this problem is kind of contrived, but let's see, how we can do well on this problem, right? So the setting is that you always start from this state. This is the initial state. You have reward everywhere except the last layer, right? So this is your goal because it has the highest reward, right? And the tricky part of this environment is that if you fall into this gray state, you're going to be stuck in the gray state, right? There's no way for you to recover back to these blue states, which we're going to call them good states. Because if you stay at the blue state all the way to the end, you're going to get the gold, right? Reward 1. But if you ever make a deviation to the gray state, we will be stuck in the gray state forever. And at the end, we're only going to receive a suboptimal reward, right? So the optimal strategy is very clear. We want to stay on the blue state all the way to the end, right? We don't want to deviate. But the tricky thing here is that there's 3 actions per blue state, right? And only one of the action will lead you to the next blue state. So your job is to actually figure out which action to take in the blue state so that you can stay in the blue states, right? So we call it combination lock because you really needed to figure out the correct combination of this green actions in order to hit the goal, right? And you can imagine that if you do a random walk, a uniform random walk in this MDP, right? What's the probability of you hitting the goal, right? It's exponentially small because the probability of hitting the correct action is roughly 1/3 if you do random walk. So we cannot really rely on random exploration to solve this problem, right? Unless you're willing to pay exponential sample complexity, then you feel free to do random walk, right? So the principle behind the exploration algorithm that we're going to talk about is, again, this optimism in the face of uncertainty. Okay, so the learning setting is actually pretty straightforward. This is the episodic iterative setting. At iteration n, so we're going to initialize the policy pi, right? And then we're going to execute that policy pi in the unknown MDP to collect a trajectory. So we just starting from this fixed state S0. So from now on, we're going to simplify the setting a little bit. We're just going to assume the initial state S0 is always fixed, right? So we execute this policy in the Markov decision process, and we get a trajectory. And then the learner will update the policy to the new policy pi n plus 1 using all the previous information. And the goal is actually to achieve some sublinear regret, right? The difference between the optimal policy's value and the difference between the value from your policy, right? Over this n iterations. Hopefully, this gap grows sublinearly with respect to n, the number of iterations. So the approach that we're gonna discuss is this optimistic model-based planning. So in high level, every iteration, you're gonna use all prior history data to estimate transitions because we don't know transitions, right? So we're just gonna use all the history data to estimate these transitions, for instance, using your favorite maximum likelihood estimator. And then we're gonna design bonus for every state action pair. So essentially the bonus will basically say that if you have high uncertainty on your transition estimator at this particular state action pair, set the bonus high. Otherwise, set the bonus low. So the bonus is sort of quantifying, the uncertainty quantification of your transition estimator. And once we have that, let's just treat our estimator and the reward plus bonus as a new Markov decision process, right? This is the best we could get at this moment, plus a little bit optimistic bonus, right? So let's just treat this as a real MDP and use our favorite planning algorithm, in this case, value iteration, for instance, right, to find a new policy. And then we execute this new policy in the real world. The hope is that, we're going to do some exploration, right, because we have reward bonus. So we're going to refine our estimation of the transition, and then hopefully we can do better in the next round. So this bonus is actually important, right? So this is like the bonus you add on the multi-unbanded algorithm as well. Okay, let me quickly go through the algorithm. I'm just going to skip this sites. Okay, so in high level, this is the algorithm, right? So for every iteration, the first step is just use the history data to maintain some statistics. So this is how many times we have visited a particular state action pair, right? The second quantity is how many times we have visited state action X state triples, right? So we just maintain these two counts. And then our estimator is just maximum likelihood estimator, right? So the probability of transiting to S prime at SA is just the ratio of the two counts, right? How many times we have visited S prime and how many times we have visited SA, right? So this is the maximum likelihood estimator. And then we're just going to design bonus, which looks a lot like the bonus you would design in multi-unbanded, right? So ignoring the log terms, the bonus will just scale in the rate of 1 over square root of number of times that we have visited this particular state action pair. All right, so that's basically the algorithm. So you do planning inside this learned model, this new model, where the transition is your MLE estimator and the reward function is the original reward plus this optimistic bonus. Okay, so you get a new policy, you execute this policy, and then you repeat this process. So what we will prove in the recitation is that in expectation, the total regret over n iterations will scale in the rate of, at least scale sublinearly in the rate of square root n. Okay, so 2 remarks here. So it's not hard to do, it's not that hard to get a high probability statement, right? So here we're just going to focus on expectation in the recitation. And the second part is that the dependence on H and S is not optimal. But the same algorithm that we just talked about can actually achieve better dependence on S already. So in other words, this is suboptimal, but the algorithm that we just presented can actually improve from this square root of S squared to just square root S. If you want to improve the dependence on H, you need to do some other stuff. Okay, so that's basically all I want to cover. And I'm also going to skip the proof sketch because we're going to talk about them in the recitation anyway. Okay, so let me just do a quick summary. So we talked about basics of Markov decision process, and then we talked about policy gradient approach. And one nice thing about policy gradient approach is that despite being non-concave, they find a global optimal solution, right? And MPG is actually pretty fast in terms of finding the global optimal policy. And then the third part, we talked about efficient exploration. And here we talked about a UCBVI algorithm. And the proof behind this algorithm is, again, this principle of optimism in the face of uncertainty. Okay, so that's all I want to talk about in part 1. Feel free to ask any questions. Otherwise, we could just take a break and we will move to the Gezer for the recitation.
Thanks, Wen. So there are some questions. I've been trying to answer them to the best of my knowledge. Maybe one question that sort of come up is whether like NPG is a first or second order method. So Wouter is asking, like, is it the same as Newton method?
So I don't think so, because we never really use the second order information about our objective function. Right, like we, yeah.
Right, but I think there's some, yeah. Oh, go ahead.
And the Fisher information matrix is basically just the Hessian of the KO divergence, right? Which the KO divergence between the two trajectory distributions that has nothing to do with the reward function, for instance.
Cool. I think maybe we should end this session because we did run over time a bit.
Yeah.
Yeah. So, yeah, thanks for staying for the session. The next part will start in Gather, like whenever you want it to start. I guess officially it's supposed to start in 1 minute, but feel free to take a break and come to Gather. And some of the questions that people are asking will actually appear on the recitation. So please do take a look and try to work through those problems. We'll be around to help out. Go find a table, find some friends, and take a stab at those practice problems. And we'll reconvene here in about 1 hour. Okay, thank you. See you in Gather.
Right, bye-bye, everyone.